Imagine the frozen outskirts of our solar system, a place where sunlight transforms into barely a faint glimmer. Here, beyond 500 astronomical units from our star, absolute darkness reigns. It takes more than 8 hours for light from the sun to reach this place. In this icy void, the orbits of dozens of small icy worlds behave very strangely. They are heavily elongated, tilted at unusual angles, and some even move backwards, against the general direction of the planets. Scientists check this using mathematical models. The chance that such an orbital arrangement happened randomly is just 0.006%. That's like winning the lottery 1 billion times in a row. Something massive and invisible commands the gravity here. A new planet? Or do our laws of physics need to be completely rewritten? Section 1. How strange patterns were discovered at the edge of the system. Let's start at the beginning. Beyond Neptune lies the Kuiper Belt, a ring of thousands of icy fragments, leftovers from the building of planets 4.5 billion years ago. Most TNOs, or trans-Neptunian objects, orbit neatly at a distance of 30-50 AU from the Sun, but there are outcasts, those that climb much farther into the scattered disk and Oort cloud regions. The first such outcast, Pluto, was found in 1930 by astronomer Clyde Tombaugh after a year of painstaking search through photographs of the night sky. Pluto became the 9th planet in textbooks. But the real mystery began in 1992, when they discovered Albion, the first true TNO beyond Pluto. Since then, their number has grown to nearly 5,000. Most are ordinary, but some are real rebels. In 2003, a team led by Mike Brown from Caltech stumbled upon Sedna. This is a small world, about 1,000 kilometers in diameter. Its orbit is a true paradox. The closest point to the Sun is 76 AU. The farthest is 937 AU. One complete circle takes 11,400 years. The orbit is strongly tilted at 12 degrees and very elongated, eccentricity of 0.85. One such object could be explained by chance. But then they found 2012 VP-113, or Biden, Gong-Gong, Liliakuhonua, and others. All of them cluster similarly. Their closest approach points to the Sun look in one direction, and their orbital nodes also cluster together. In 2016, Brown and his colleague Konstantin Batygin published a paper in Nature. They calculated the orbits of 17 of the strangest TNOs. The results shocked everyone. The probability of random coincidence, 0.0006%, or one chance in 1.7 million. An invisible gravitational conductor is needed. This body has a mass of 5 to 10 Earth masses, later refined to 7 to 17, on an elongated orbit with a semi-major axis of 400-800 AU, a period of 10 to 20,000 years, and an inclination of 15 to 25 degrees. Such a giant explains everything through the Leadoff-Kozai mechanism. In a three-body system of Sun-Theano giant, inclination transforms into eccentricity. Models perfectly reproduce real orbits. Planet 9 was predicted in a small patch of sky near Orion, but it's not visible. Section 2. Why Planet 9 is so difficult to detect. The problem is light. The planet doesn't shine by itself. It reflects faint sunlight. At a distance of 500 AU, brightness doesn't drop like 1 over distance squared, but like 1 over the 4th power of distance, millions of times weaker. For a planet with albedo of 0.1, like Neptune, the apparent magnitude would be 24 to 25. This is at the limit of the best telescopes. Surveys like ZTF, Dark Energy Survey, and Pan-STARRS 1 scanned the predicted region for years. Nothing. But planets emit heat. Even cold giants like Neptune glow in the infrared range like a black body at a temperature of 30-40 Kelvin. This is where the key hides. Section 3. Breakthrough in Old Data. IRAS and AKARI. In 2225, a team from Taiwan, Professor Tomogoto from National Tsinghua University and his graduate student Terry Longfan, decided to search for the heat of Planet 9 in the archives. They took 2 infrared all-sky surveys. IRAS, a NASA satellite from 1983, the first ever survey of the entire sky in infrared light. The sensors were cooled with liquid helium to extremely low 2.5 Kelvin to remove the instrument's own heat. On wavelengths of 60-100 microns, they found 350,000 new sources: galaxies, asteroids, dust clouds, even zodiacal dust. AKARI, a Japanese satellite from 2006 by JAXA. The word AKARI means light. Improved resolution, 9 arcseconds compared to 30-90 for IRAS. It covered the same wavelengths plus 160 microns. Over 23 years between the missions, 2.4 million objects accumulated. Scientists applied a strict filter for Planet 9. Mass of 7 to 17 Earth masses. Diameter of 2 to 4 Earth radii. Orbit. Closest point 280 plus 60 AU. The farthest point, 800, 1,220 AU. Speed on the sky, about 2 arc minutes per year at a distance of 500, 700 AU. There, the planet slows down and spends 90% of its time. Temperature and brightness match the black body model. The computer processed millions of points. 13 candidates remained. Terry Fan manually checked each one. 1-1. On the IRAS 60 micron image in the upper left corner, 7 pixels slightly warmer than the background, at 2 sigma above noise. In AKARI 23 years later, this spot shifted 47.5 arcseconds to the southeast, like 1.5 lunar diameters. The energy flux perfectly matches a planet of 10 Earth masses at 620 AU distance. The position coincides with the cluster of TNOs. Professor Goto joked, if confirmed, Terry defends his doctorate tomorrow. But Mike Brown and Badajian are cautious. The candidate's orbit inclination is around 35 degrees, while models suggest a maximum of 25. The complete trajectory hasn't been reconstructed due to sparse observations. Plus, in AKARI, by parallax method, they found 2 more suspicious objects. The paper is being prepared for archive. Section 4. The Vera C. Rubin Observatory will render. Judgment. Now it's the turn of Vera C. Rubin Observatory in Chile. First light, 2025. The LSST camera, 3.2 billion pixels. Field of view, 9.6 degrees. Brightness limit, magnitude, 27.8. Over 10 years, it will survey the entire sky 2,000 times per square degree, 20 terabytes of data per night, 60 petabytes total. Solar system mode will find 100 times more TNOs, down to magnitude 26. Brown said directly, "Give me money to search for Planet 9. I'll build a copy of Rubin." The planet should light up as a point of magnitude 24.5. In 1 to 3 years, either they'll catch its movement against the background of stars, or exclude 80% of possible space. The ZM belt will also be tested. If there are too many objects, and they're evenly distributed, this signals a collective effect. Section 5. If Planet 9 doesn't exist. 3 alternative explanations. Let's assume Rubin finds nothing. What then? Alternative 1, the Zderik-Madigan belt. In 2024, Alexander Zderik and Anne-Marie Madigan proposed an analog of galactic bars. 2/3 of spiral galaxies, including our Milky Way, have a central bar. Millions of stars on X1 orbits around Sagittarius A create a common gravitational field without a single leader, like a flock of birds or an ant colony. Scale it down, 1020 Earth masses and TNOs at 100-500 AU. Resonances align the clusters of perihelions. LSST will show Planet 9 would leave voids, while a belt fills space evenly. Alternative 2, a captured primordial black hole. In 2020, Jakob Schultz and James Unwin suggested these relics of the Big Bang were born from density fluctuations in the first seconds. They have no lower mass limit like stellar black holes. A black hole with Earth's mass has an event horizon the size of a centimeter, like a football. Captured early in the solar system's youth from nearby space or from the Oort cloud. Gravity identical to Planet 9 but invisible without accretion or microlensing. This connects the problem to dark matter. Maybe primordial black holes make up part of it? Alternative 3, MOND, Modified Newtonian Dynamics. In 1983, Mordechai Milgram said, "At accelerations below 1/1,000,000th of a meter per second squared, gravity strengthens. The gravitational pull from the galactic center aligns TNO orbits without a new planet." In 2023, Kyu-Hyun Chai showed perfect match with the clusters. MOND is controversial on the scale of galaxy clusters, but the solar system's edge is an excellent laboratory. Section 6. What does the event horizon of our system hide? If they find Planet 9, 9 planets will return to textbooks. A super-Earth type will be revealed. Neptune migration will be rewritten. A belt will show. Self-gravitating disks work from stars to supermassive black holes. A black hole will tie the sun to dark matter cosmology. MOND will hint at replacing general relativity. What's scarier? A new planet returning a schoolbook picture of the world, or gravity that works differently from Newton's apple to galaxy spirals? The Rubin telescope already turns its eye every night. The universe quietly says, your model is incomplete. The TNOs whisper about system birth, world isolation, maybe even about planets with life ejected into the void. Subscribe to be the first to know what Rubin catches. This mystery at the edge of our solar system represents one of the greatest unsolved puzzles in modern astronomy. Whether we discover Planet 9, an unseen belt of objects, a primordial black hole, or find that gravity itself needs revision, the next few years will reshape our understanding of the cosmos. The Vera C Rubin Observatory stands ready. The data streams in nightly. And somewhere out there, beyond Neptune's orbit, in the frozen darkness, the answer waits to be found. The universe is not done surprising us, not by a long shot.